Before the existence of stars, planets, and even light itself, there was a concept that has mystified humanity: nothingness. What does it truly mean for something to come from nothing? Join us as we delve into what may have existed before time and space. The period before the Big Bang is a tantalizing enigma that has intrigued scientists and cosmologists alike. Many theories attempt to grapple with what preceded this monumental event. One of the most compelling ideas is the concept of cosmic inflation. This theory suggests that, in the very first moments after the Big Bang, the universe underwent an incredibly rapid expansion. Although this primarily addresses what happened right after the Big Bang, rather than before it, it hints at the conditions that could have led to our universe's inception. Another perspective posits the existence of a singularity. A singularity is a point in which gravitational forces compress matter to infinite density prior to the Big Bang. If our universe originated from such a singularity, then all physical laws as we know them break down, making it challenging to define what before meant in this context. This notion implies a history where time itself may not have existed in any recognizable form, departing from our conventional understanding. Some scientists and researchers advocate for the cyclic model of a universe, where the cosmos undergoes endless cycles of expansion and contraction. In each cycle, the universe expands from a hot, dense state, only to eventually collapse back into itself, leading to a new Big Bang. This model suggests not only a past before our current universe, but a potentially infinite series of universes preceding it, each with their own unique variations. Then there's the concept of the multiverse, which theorizes that our universe might just be one of countless others, each with different physical laws and constants. In this scenario, the Big Bang could be seen as a bubble popping into existence in a larger sea of universes. Each of these theories offers distinct insights into the mind-boggling question of what came before our universe, emphasizing the complexity and the frontier nature of cosmological science. Quantum fluctuation introduces a layer of complexity in our understanding of a universe's inception. At the heart of these fluctuations lie the principles of quantum mechanics, a field that describes behavior on the tiniest scales, such as atoms and subatomic particles. In this realm, uncertainty reigns. Particles and energy can appear and disappear seemingly out of nowhere, driven by the inherent unpredictability of quantum states. This phenomenon suggests that the fabric of reality is far more dynamic than we might have previously thought. When scientists consider the origin of the universe, a notable hypothesis is the Big Bang theory, which posits that the universe began as an incredibly hot and dense state. Yet, if we apply the principles of quantum mechanics to this moment of creation, we are left grappling with the idea that during the first instance following the Big Bang, minute fluctuations in energy could have led to the uneven distribution of matter and energy we observe today in the cosmos. Instead of a singular, smooth beginning, these fluctuations hint at a chaotic, bubbling realm of possibilities, where tiny random variations could have been amplified over time to shape galaxies and cosmic structures. These quantum variations also raise intriguing questions about the very nature of creation itself. If the universe could emerge from a vacuum, with energy sparking into existence from nothingness, what does that say about existence? This challenges traditional views that see a clear boundary between nothing and something. It proposes that nothing is not actually an empty void, but a vibrant field teeming with potential, where fluctuations can lead to profound outcomes. Moreover, the implications of quantum fluctuations extend beyond our past into our understanding of the universe's fate. The ongoing dynamics of these fluctuations, as postulated by theories like cosmic inflation, imply that even now the universe is influenced by these subtle energy changes. The universe could still be unfurling in ways we barely comprehend, continuously shaped by quantum events. This interplay between the tiniest movements and the grandest structures in the universe tantalizingly underscores the interconnectedness of existence. The multiverse theory suggests that our universe is just one of potentially countless others, each with its own distinct characteristics and physical laws. This concept opens intriguing avenues for exploring the conditions that may have existed before the Big Bang. If multiple universes exist, it raises a possibility that some of these universes could provide clues about the nature of reality prior to our universe's beginning. One of the fascinating implications of the multiverse theory is that it allows for various scenarios concerning the origins of universes. Some models propose that universes can emerge from the collision of other universes. This idea leads to the suggestion that our universe might not have simply burst into existence, but could have been born from interactions in a vast cosmic landscape. By studying these interactions, scientists might glean insights into the state of the universe before its inception, including parameters that governed it. Additionally, the multiverse offers a framework for considering different laws of physics that could have prevailed before the Big Bang. Each universe in the multiverse might have varied constants and forces, which would in turn influence the conditions leading up to their respective Big Bang events. Understanding these different sets of physical laws allows researchers to hypothesize about how the Big Bang occurred in our universe, as well as how other universes may have experienced their own distinct beginnings. On a more speculative note, the conditions before the Big Bang might be hidden within quantum fluctuations in a multiverse context. If our universe originated from a quantum state, exploring the dynamics of these fluctuations across several universes could uncover what precedes a familiar cosmic expansion. As researchers continue to unravel the intricacies of the multiverse theory, we may ultimately gain deeper insights into one of the most profound mysteries of cosmology, what existed before the universe we call home came into being. Cyclical universe models suggest that the universe undergoes an eternal series of expansions and contractions, effectively recycling itself through time. The central idea here is that, after reaching a maximum size, the universe begins to collapse under its own gravity, eventually leading to what is known as the Big Crunch. This collapse is thought to compress all matter and energy back to an incredibly hot and dense state, similar to the conditions that might have existed just before the Big Bang. One of the most prominent versions of this theory is the oscillating universe model. In this framework, the universe experiences a continuous cycle of expansion, contraction, and rebirth. Each expansion phase, often referred to as a Big Bang, would create a new universe shaped by the remnants of the previous cycle. This continuous loop proposes that the universe is not just a one-time event, but rather a lasting entity that transforms and evolves over infinite time. In some variations of cyclical models, like the one proposed by string theory, the universe could also experience cosmic bouncing, where the universe avoids singularities entirely. Instead of collapsing into a point of infinite density, the universe's expansion would slow down, halt, and then reverse into a contraction phase, initiating a bounce back into an expansion phase. This model accommodates the current understanding of cosmic expansion while incorporating gravitational and quantum effects. These principles challenge a conventional notion of a linear universe that began singularly and will end in a freezing fate or Big Rip. Instead, they explore fascinating possibilities of cosmic longevity, suggesting that not only does a universe change over time, but it also persists through an endless cycle of destruction and renewal, eternally crafting new realities from the ashes of the old. Cosmic inflation is a fascinating idea that describes the very early moments of our universe's existence. Imagine a period just after the Big Bang when the universe expanded at an astonishing rate, exponentially stretching in size. This rapid expansion, which occurred within a fraction of a second, helped smooth out any irregularities and set the stage for the cosmos as we know it today. It provides a framework for understanding how the universe reached its large and uniform state as it grew from a hot, dense point to a vast, cooler expanse. Now, when we consider the universe before this expansion, things become intriguing. Traditional models of the Big Bang suggest that time and space, as we know them, originated from that singular event. However, cosmic inflation opens up possibilities about conditions and structures that might have existed prior to our universe's explosive birth. Some theories suggest that our universe could have emerged from a prior cosmic state, or even from fluctuations in a quantum vacuum, a field that exists even in the absence of matter. In these theoretical landscapes, the universe isn't necessarily the first of its kind. It may be one of many oscillating universes, or part of a multiverse where different regions exist with varying physical laws. These ideas challenge our understanding of time, because without a clear beginning, we ask ourselves what before even means in this context. It evokes a sense of wonder about what the universe was like, and raises profound questions about the nature of existence itself. As researchers delve deeper into cosmic inflation, they explore its implications for understanding reality itself. It suggests a universe that is not static, but dynamic and ever-changing, shaped by complex processes that may stretch far beyond our current perception of time and space. This interplay between cosmic inflation and the theories of existence before our universe continues to inspire questions and excite imagination across the fields of cosmology and physics. Singularities are extraordinary points in the fabric of space and time where the usual laws of physics break down. They are typically associated with very dense objects. In the context of the universe's beginning, the most famous singularity is the one believed to have existed at the moment of the Big Bang. Here, all matter and energy were concentrated into an infinitely small point, resulting in extreme temperatures and densities. This singular state birthed the entire universe as we understand it, marking the inception of time and space approximately 13.8 billion years ago. As we delve deeper into the nature of singularities, they also appear in the center of black holes. These enigmatic regions create immense gravitational pulls so strong that not even light can escape. When stars reach the end of their life cycles and collapse under their own gravity, they form black holes where singularities reside. While the implications of singularities this way reveal aspects of our universe's life cycle, they also raise questions about the ultimate fate of matter, energy, and even information itself. Thinking about precursors to the universe, singularities invite us to consider theories like cosmic inflation. This concept proposes that, shortly after the Big Bang, the universe underwent an exponential expansion. Some researchers suggest that the dynamics of singularities could play a role in understanding what might have preceded the Big Bang itself, or how the universe evolves past the singularities within black holes. Thus, singularities serve not only as a cornerstone in understanding the universe's origins, but also as a window into complex processes that shape its evolution. They challenge our perspectives, pushing the boundaries of what we know, and inviting us to ponder the mysteries that lie beyond our current scientific grasp. String theory presents a fascinating framework that seeks to unravel the mysteries of the universe, particularly the enigma of what existed before the Big Bang, the moment that marked the beginning of everything we know. At its core, string theory suggests that the fundamental building blocks of the universe are not point-like particles, as traditionally thought, but rather tiny vibrating strings. These strings exist in multiple dimensions beyond the familiar 3 dimensions of space and one at a time. This opens up a new way of thinking about the cosmos and its origins. By proposing additional dimensions beyond our common experience, string theory provides a potential explanation for conditions that may have existed prior to the Big Bang. It suggests that these extra dimensions could represent various states of energy and existence, where the universe was in a highly dense and chaotic state. In this pre-Big Bang scenario, the string could interact in ways we are still striving to comprehend, potentially giving rise to the explosive event that initiated our observable universe. Through this lens, string theory does not seek to locate a definitive before, but instead offers a framework for reconstructing the universe's earliest moments. Moreover, in seeking to unify all fundamental forces in nature, string theory provides insights that are not merely theoretical, but can also influence how we approach questions about the universe's origin. For instance, phenomena related to black holes and the fabric of space-time could be better understood through the principles of string theory. By contemplating how gravity interacts with quantum mechanics, researchers hope to glimpse the conditions that could have set the stage for the Big Bang itself, potentially bridging our understanding of what might precede our universe. While string theory is still not universally accepted and remains a topic of debate among physicists, its implications encourage scientists to rethink foundational concepts of time, space, and existence. What came before is no longer a simple void, but a vibrant tapestry of possibilities, governed by the laws of string dynamics, inviting relentless curiosity and exploration into the very nature of reality itself. What came before is no longer a simple void, but a vibrant tapestry of possibilities, governed by the laws of string dynamics, inviting relentless curiosity and exploration into the very nature of reality itself. This investigation holds the potential to revolutionize our understanding of the universe's origins, offering tantalizing glimpses into the tapestry woven by the strings of existence. Dark matter and dark energy play pivotal roles in our understanding of the universe's origins and its ongoing evolution. Despite being unseen, they significantly influence the structure and behavior of the cosmos. Dark matter, which is estimated to constitute approximately 27% of the universe, serves as a gravitational framework, ensuring that galaxies, clusters of galaxies, and even larger structures remain intact. Its existence is inferred from the gravitational effects on visible matter rather than being directly observable. Without dark matter, galaxies would not have a necessary gravitational pull to hold together their stars and other components, leading to an entirely different cosmic landscape. On the other hand, Dark energy, which makes up about 73% of the universe, has been a source of curiosity and intrigue among astronomers. This mysterious force is believed to be responsible for the accelerated expansion of the universe, a phenomenon first noted in the late 20th century, when distant supernovae were observed to be moving away from us at an increasing velocity. The nature of dark energy is still largely unknown, and it challenges our traditional understanding of gravity and the fabric of space-time itself. The combination of dark matter and dark energy changes the course of cosmic history. After the Big Bang, dark matter helped to clump together matter, leading to the formation of the first stars and galaxies. Meanwhile, as the universe expanded, dark energy emerged, overpowering the gravitational attraction of matter and driving galaxies further apart. This interplay suggests a dynamic cosmos, where invisible opponents greatly influence visible phenomena. Delving into these concepts invites fundamental questions about the universe itself. What are the true identities of dark matter and dark energy? Are they merely product of the equations of physics, or do they represent a deeper layer of reality yet to be discovered? As research continues, scientists hope to unravel the mysteries that dark matter and dark energy present, bringing us closer to a comprehensive understanding of the cosmos and our origins within it. The idea of a baby universe is a fascinating concept within the framework of cosmology, arising from our efforts to understand the origins and development of the universe. This notion suggests that, much like the universe we inhabit, smaller self-contained universes can emerge from a parent universe, each exhibiting its own set of physical laws and constants. This theory aligns with certain interpretations of cosmic inflation, wherein the rapid expansion of space shortly after the Big Bang could give rise to pocket universes or baby universes. Current cosmological theories propose that, during the early moments after the Big Bang, fluctuations in energy could cause regions of space to inflate dramatically. Some of these regions might continue expanding and evolve into distinct universes, each potentially disconnected from one another, yet emerging from a shared cosmic origin. This scenario raises intriguing questions about the nature of reality, existence, and whether there might be an infinite number of these baby universes, forming a multiverse beyond the limits of our observable universe. One of the most enthralling aspects of the baby universe concept is the implications it carries for quantum mechanics. In quantum theory, particularly in Stephen Hawking's discussions about black holes, the idea emerges that black holes might not only capture matter but could also facilitate the birth of new universes. According to this perspective, the singularity at the center of a black hole could act as a gateway, where the conditions are ripe for a fresh universe to emerge, potentially replete with its own specific laws of physics. As researchers delve deeper into these theories, they continue to explore how these baby universes might connect with a broader structure of reality. Questions about the fate of these universes, their potential for interaction with our own, and the fundamental laws that govern them captivate scientists and philosophers alike. The more we learn, the more we realize how much remains to be discovered about the cosmos, and the concept of baby universes offers a remarkable glimpse into the possibly boundless nature of creation itself. When we refer to nothing, we are diving into one of philosophy's most profound and intriguing concepts. Nothingness implies the absence of anything that can be perceived, measured, or even imagined. It stands in stark contrast to existence, which is marked by entities and phenomena, everything that fills a universe. This dichotomy raises deep questions about the nature of reality itself and our understanding of existence. The idea of nothingness challenges us to think about the very fabric of existence and prompts us to ask what it means to be. For instance, in quantum mechanics, there is a fascinating suggestion that even what we perceive as empty space is teeming with potential. Particles may not be permanently visible but can arise, queue, and disappear from this so-called nothingness. This leads to the conclusion that, even in the absence of matter and energy, the potential for creation lurks just beneath the surface, giving us a glimpse into a universe filled with possibilities. Philosophically, the concept of nothing invites reflection on existence's value and significance. If we were to grasp the fullness of nothing, it could instill a greater appreciation for everything that surrounds us, the stars, the planets, and even the air we breathe. Life becomes a remarkable phenomenon against the backdrop of emptiness. Each tiny particle in our bodies, every blade of grass, and all the expansive cosmos stand as testaments to existence where there could have been none. Our explorations into nothingness ultimately push the boundaries of what we know. They stir curiosity and wonder, inviting us to consider the very nature of reality. If nothingness can exist and can transition into something, it poses fundamental questions about creation, the universe's origins, and our place within it. In grappling with these ideas, we begin to understand that existence is not merely about being present, but also about appreciating the intricate dance between existence and potential what could be even in the vast realms of nothingness. Philosophers have grappled with the notion of nothingness for centuries, pondering its implication for existence, reality, and meaning. In ancient Greece, thinkers like Parmenides argued that nothingness could not truly exist, because to speak of nothing is to imply a lack of being. For Parmenides, existence itself was the only certainty, and any idea of nothingness was inherently contradictory. This philosophical inquiry laid the groundwork for later explorations of existence versus non-existence. As philosophy progressed through the ages, figures like René Descartes brought a new perspective with his famous assertion, "I think, therefore I am." Descartes suggested that the act of doubt or thought proved the existence of the self, distinguishing existence as a fundamental quality. This assertion further highlighted the tension between being and nothingness, that one must acknowledge existence to even contemplate the void. The challenge remained: how does one conceptualize what it means to exist in a universe that could also embody the absence of all things? The existentialist movement in the 20th century brought nothingness to the forefront, particularly with philosophers such as Jean-Paul Sartre. Sartre posited that nothingness plays a critical role in shaping human existence. He argued that individuals face the daunting freedom of choice, creating meaning in an otherwise indifferent universe. By recognizing that life lacks inherent purpose, one must confront the emptiness that surrounds existence and ultimately take responsibility for their choices. This dialogue between nothingness and existence continues to resonate in contemporary thought. Throughout history, the exploration of nothingness has stirred deep philosophical discussions about what it means to exist. From Parmenides to Sartre, each philosopher contributed unique insights, shaping our understanding of the profound complexities that arise when we consider both being and the absence of being. This enduring interest in nothingness reveals not only the limits of human understanding, but also the relentless quest to find meaning amidst the void. The debate over nothing significantly complicates our discussions about the universe's origins, particularly in the realm of cosmology and philosophy. Nothing is a concept that elicits more confusion than clarity, especially when we consider that in physics, even the emptiest regions of space still contain quantum fluctuations. These fluctuations suggest that nothing is not truly devoid of activity or potential, challenging our traditional notions of emptiness. Many scientists and philosophers argue about the nature of nothingness. If we consider that nothing could give rise to something like the universe, we must grapple with the potential mechanisms involved. Theories such as quantum mechanics propose that particles can emerge spontaneously from a vacuum, which adds a fascinating layer to the question of how the universe began. This suggests that the very act of creation could be a natural occurrence within a realm we might not yet fully understand, blurring the boundaries between existence and non-existence. Further complicating discussions are the philosophical implications tied to nothing. Different philosophical traditions present various interpretations of existence, and these perspectives can influence scientific inquiry. For example, if nothing is a state of being without properties, what does that imply about our understanding of time, space, and causality? These philosophical angles force scientists to consider not only empirical evidence but also foundational assumptions regarding existence and reality itself. As we delve deeper into these questions, the interplay between science and philosophy becomes evident. The debates surrounding nothing push us to reconsider our models of the universe's origins, leading to more profound inquiries that inspire both scientific innovation and existential reflection. In this way, nothing becomes a paradoxical catalyst that fuels exploration into the very essence of our universe. Existentialism delves into the nature of existence and the individual's experience in a seemingly indifferent universe. In cosmological debates, the concept of nothingness can be particularly perplexing, as it challenges our understanding of being and reality. Philosophers such as Jean-Paul Sartre and Martin Heidegger explored how the recognition of nothingness can lead to profound existential crisis. They asserted that the awareness of nothingness strips away illusions, leaving individuals to confront their existence in a universe that may appear devoid of inherent meaning. This philosophical framework encourages us to ponder our significance within the cosmos. When we consider the vastness of space and the possibility of cosmic emptiness, Existentialism helps articulate that nothingness is not simply an absence, but also a crucial aspect of understanding existence itself. The void can represent potential, an openness where new ideas and realities might emerge. It prompts us to question what it means to exist, urging us to find or create meaning rather than accept a predetermined cosmic order. In cosmology, these existential questions lead to rich discussions about the origins of the universe and our place within it. Theories surrounding the Big Bang often brush against the concept of nothingness, as they explore what existed before this initial expansion, and whether it was indeed a void or something yet to be defined. By engaging with these profound inquiries, existentialism invites scientists and philosophers alike to explore the idea that our search for meaning can flourish even in the face of cosmic silence. Ultimately, the existentialist perspective serves as a bridge between philosophical contemplation and scientific inquiry, encouraging a dialogue about how we grapple with the implications of nothingness in the grand tapestry of the universe. Through this lens, nothingness transforms from a mere absence into an invitation for exploration as we navigate our journey through existence and the mysteries that lie beyond. The concept of everything emerging from nothing invites a cascade of philosophical questions that delve deep into the nature of existence itself. For centuries, thinkers have grappled with what it truly means for something to come from nothing. If the universe, with its galaxies, stars, and intricate life forms, sprang into being from a state devoid of matter or energy, one might ponder the very essence of creation. What does that imply about causality and the beginning of time? How can something emerge if there was once nothing? This notion also prompts us to question the nature of nothingness itself. Is it merely a vacuum, an absence, or does it possess properties of its own? The philosopher Martin Heidegger famously mused on the idea of being in nothingness, suggesting that understanding existence requires us to grapple with non-existence. Such reflections challenge us to explore whether nothing can truly be considered a state, or if it is merely defined in relation to something. This leads us to contemplate the limits of human understanding and language. How can we describe absence using terms rooted in presence? Then what does that mean for meaning in our lives? Is meaning something we impose onto the universe, or does it arise inherently from the interactions within it? Questions about the randomness of existence versus a predetermined order provoke reflections on whether there is a guiding force or intention behind this remarkable unfolding of reality. Ultimately, these inquiries do not just reside in abstract thought, they resonate with our experiences and beliefs. They invite us to consider our own place within this vast cosmos and encourage a deeper examination of the very fabric of reality. Exploring the emergence of everything from nothing illuminates our understanding of existence, challenging us to reflect on the most profound questions of life, purpose, and the universe we inhabit. Eastern philosophies, particularly those emerging from traditions like Hinduism and Buddhism, often embrace a concept of pre-existence that aligns with ideas of cycles, reincarnation, and unity with the cosmos. Within Hindu thought, the belief in the soul or Atman suggests that each individual has existed in various forms throughout countless lifetimes. This journey is deeply intertwined with the concepts of karma and dharma, where one's actions in past lives shape current and future experiences. Life is seen as a continuum, an expansive cycle of birth, death, and rebirth, pushing individuals towards the ultimate goal of liberation known as moksha, a state of oneness with the divine. In contrast, Western philosophies, particularly those rooted in Judaism, Christianity, and Greco-Roman thought, typically attach a more linear understanding of existence. Pre-existence is often viewed through the lens of a singular life meant to prepare individuals for an eternal afterlife. For instance, in Christian theology, the soul is believed to be created uniquely by God at the moment of conception, with one's earthly life serving as a test for eternal destiny. Personal identity in this lens is tied closely to actions within a single lifetime, emphasizing notions of salvation and moral judgment rather than cycles of existence. When exploring these ideas, fascinating variations emerge within each tradition. For Buddhists, the focus lies not only on the collective past lives, but also on the desire to transcend suffering through enlightenment and eventual liberation from the cycle of rebirth. This focus on psychic transformation underscores the shared interconnectedness of all beings, prompting individuals to cultivate compassion and mindfulness in the present. Both philosophical traditions ultimately seek to offer insights into the nature of existence and the human experience, yet they arrive at remarkably different interpretations of pre-existence. The exploration of these concepts can lead to rich discussions about the essence of identity, purpose, and the interconnectedness of all life, revealing a diverse tapestry of human thought that continues to captivate minds seeking to understand their place in the universe. The notion of something from nothing presents a fascinating challenge to long-held beliefs about causality. Traditionally, we understand that every effect must have a cause. This principle is deeply embedded in our understanding of the universe, where events lead into one another in a chain of cause and effect. However, the concept of creating something from nothing disrupts this neat distinction, leading us to question the very foundations of how we perceive existence. Take, for instance, modern theories in cosmology that suggest the universe itself may have emerged from a state of nothingness. In this context, nothing doesn't imply an empty void, but rather a quantum vacuum filled with energy fluctuations where particles could spontaneously arise. This idea of spontaneous generation defies conventional logic. If existence can emerge without a pre-existing cause, then the linear narrative of cause and effect becomes more complex and nuanced. Philosophers and scientists grapple with this phenomenon, as it implies that the universe might not adhere strictly to our intuitive understanding of causality. Such insights stimulate rich discussions about the nature of reality, urging us to broaden our conceptual frameworks. Additionally, they raise profound questions about the origins of everything, from particles to galaxies, and even the laws of physics themselves. As we delve into these inquiries, we find ourselves at the intersection of philosophy, physics, and metaphysics. The paradox of something from nothing not only challenges our views of causation, but also invites a deeper exploration of existence, leading to a richer understanding of the cosmos and our place within it. The philosophical concept of the void can play a significant role in deepening our understanding of the early universe. In cosmology, scientists often refer to the void as the absence of matter, an empty space where nothingness seems to prevail. This notion aligns intriguingly with the early conditions of our universe, which, according to theories, was once a vast expanse of nearly uniform energy and radiation before the emergence of matter and structure. At the very beginning, shortly after the Big Bang, the universe was in an incredibly dense and hot state where fundamental particles barely existed. As it expanded, the void grew more pronounced. Understanding this void helps scientists explore the properties of dark energy and matter. In fact, the void is essential for the formation of cosmic structures like galaxies, as they emerge from the gravitational clumping of matter within an otherwise empty space. This layering of density across the cosmos illustrates how the void is not just absence, but also a crucial component in cosmic evolution. Moreover, the philosophical implications of the void prompt deeper questions about existence and reality itself. In contemplating the void, we reflect on the transition from nothingness to abundance that marks our universe's history. The tension between nothingness and substance invites discussions about the nature of creation, the laws governing the universe, and the boundaries of our scientific knowledge. These explorations enrich our scientific perspective by merging abstract thinking with empirical evidence. In exploring such philosophical dimensions, we can appreciate that the universe's intricate design is shaped not only by what exists, but also by what does not exist. This multidimensional approach fosters a more profound comprehension of the early universe, merging scientific inquiry with philosophical reflection, ultimately enriching our quest to understand where we came from and how the cosmos came to be. Human concepts of creation and destruction play a significant role in how we interpret the origins of the cosmos. Throughout history, civilizations have crafted narratives about the universe's beginnings that often reflect their own experiences with creation and the cyclical nature of life. In many cultures, the act of creation is deeply intertwined with mythology and spirituality, serving as a way to understand the vast mystery surrounding us. These narratives embody the hope of new beginnings, often symbolized by the birth of stars or the emergence of whole galaxies from cosmic dust. On the flip side, the concept of destruction adds another layer to our understanding of cosmic events. Destruction is not simply an end, it is frequently seen as a precursor to new creation. For instance, the death of a massive star culminates in a spectacular explosion known as a supernova, which disperses elements into space, eventually contributing to the formation of new stars and planets. This interplay between creation and destruction provides insight into the universe's cyclical processes, where endings pave the way for beginnings. As we study cosmic beginnings through the lens of science, such as the Big Bang Theory, these human concepts shape how we relate to the enormity of the cosmos. The Big Bang, often referred to as the moment our universe began, resonates with human notions of birth and creation, while the eventual fate of the universe, whether it ends in collapse or expansion, sparks reflections on destruction and renewal. By examining these themes, we can appreciate both the scientific and philosophical dimensions of the cosmos, leading to a richer understanding of not just where we come from, but also what it means to exist. Ultimately, our interpretations of the universe are colored by these fundamental human experiences. They help us frame questions about existence, purpose, and the intricate dance between creation and destruction that is inherent in nature. As we look at the stars and contemplate our origins, these themes remind us that our place in the universe is not merely an observation, but a profound connection to the very fabric of what's possible in the grand scheme of cosmic history. The early universe was a place of extremes, characterized by conditions vastly different from anything we experience today. During the Planck era, which lasted from 0 to approximately 10 to the minus 43 seconds after the Big Bang, the universe was incredibly small, incredibly hot, and unimaginably dense. At this time, all the physical forces we know, gravity, electromagnetism, the strong force, and the weak force, were unified into a single force, meaning that the laws of physics as we understand them were not yet distinguishable from one another. The temperatures were so overwhelming, estimated to be around 10 to the 27th degrees Celsius, that the very fabric of space and time began to behave in ways that challenge our understanding of physics. At these energy levels, fundamental particles like quarks and electrons were in a state of constant flux. Matter as we recognize it had not yet formed. Instead, the universe was filled with a hot, dense soup of energy and radiation. Where particles were continually being created and annihilated, this chaotic environment is thought to have set the stage for the eventual separation of forces as the universe cooled, allowing particles to take on distinct identities and the first building blocks of matter to emerge. As the universe expanded and cooled further, it transitioned out of the Planck era into the next phase, known as the Grand Unification era. However, the distinctive characteristics of the Planck era continue to intrigue scientists today. The laws governing this epoch are believed to have profound implications for our overall understanding of the universe, including insights into the origins of space and time. One of the outstanding questions is whether the theory of quantum gravity can successfully describe this early moment, an endeavor that could unlock the secrets of the universe's birth and provide a more comprehensive understanding of its evolution. Ultimately, the conditions during the Planck era were foundational, paving the way for everything that followed. The mysteries wrapped up in this seemingly brief moment remind us just how much more there is to discover about our universe's earliest days, teasing the boundaries of modern physics and our comprehension of reality itself. During the Planck epoch, which occurred within the first 10 to the negative 43 seconds after the Big Bang, the very fabric of time and space operated under rules that are unfathomable to our everyday experience. At this minuscule moment, all the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified. The energies involved were so extraordinarily high that quantum effects dominated, and space-time itself was likely turbulent and chaotic, unlike the smooth, predictable nature we observe today in our current understanding. Time flows steadily, and space is described by the dimensions we can perceive. However, at the Planck scale, the granularity of space-time becomes significant. We can envision time not as a continuous river, but more like a series of discrete moments or events that are interspersed with quantum fluctuations. This means that the conventional beginnings and ends of events may lose their clear definitions, challenging our notions of causality and sequence. Moreover, distances in space-time itself seem to be on a scale that our senses and current physics cannot readily grasp. The dimensions we take for granted were either non-existent or entirely different, as space-time may have been so compact that it was hard to distinguish between the effects we now identify as time and space. Theoretical physicists suggest that what we understand as the fabric of the universe was fluid and pliable, continuously influenced by quantum uncertainties. Thus, comprehending the universe during the Planck epoch requires grasping a reality where physics diverges sharply from the laws governing our macroscopic world. As the universe expanded and cooled, these unified forces began to separate, and space-time settled into the more structured framework we are now familiar with. This transformation set the stage for the rich tapestry of cosmic events that followed, leading ultimately to the universe we inhabit today. High-energy physics plays a pivotal role in exploring the mysteries of the universe, particularly when it comes to understanding the moments leading up to the Big Bang. This branch of physics investigates the fundamental particles and the forces that govern their interactions at energies far beyond what we experience in our everyday lives. By examining these high-energy scenarios, scientists can recreate conditions similar to those thought to exist in the early universe, providing valuable insights into its origins. When we consider the moments prior to the Big Bang, we venture into territory where current physical theories become particularly vital. Models such as quantum field theory allow physicists to probe the behaviors of fundamental particles when energy densities were extraordinarily high. This exploration can reveal how the fundamental forces, like gravity and electromagnetism, may have operated in concert during that chaotic period. Specifically, high-energy collisions in particle accelerators such as a Large Hadron Collider simulate the extreme conditions of the early universe and can help us uncover clues about particle interactions that might have taken place at that time. Furthermore, high-energy physics delves into phenomena like the inflationary model, which posits a rapid expansion of space just after the Big Bang. This model suggests that quantum fluctuations in the energy field could have seeded the large-scale structures we observe in the universe today. By studying these fluctuations and the properties of particles at high energies, researchers aim to paint a clearer picture of how the universe evolved from its initial singularity. As scientists continue to push the boundaries of high-energy physics, each new discovery adds a layer to our understanding of cosmic history. While many questions about the events before the Big Bang linger, the insights gained from high-energy physics bring us closer to unraveling the intricate tapestry of the universe's beginnings. Scientists have developed several inventive methods to study the conditions of the early universe, all while navigating the challenges posed by limited observational evidence. One of the primary tools in this quest is the field of cosmology, which combines theoretical models with available data to reconstruct the universe's infancy. By analyzing the cosmic microwave background radiation, the afterglow of the Big Bang, researchers can glean vital clues about the universe just a few 100,000 years after its birth. This faint radiation is remarkably uniform, but it contains tiny fluctuations that reflect variations in density, providing insights into how matter was distributed throughout the developing cosmos. In addition to analyzing cosmic microwave background radiation, scientists utilize simulations and models based on the laws of physics to understand early universe conditions. These models rely on principles of general relativity and particle physics to replicate the environment just moments after the Big Bang. By adjusting various parameters in their simulations, researchers can see how different conditions could lead to the formation of elementary particles, atoms, and eventually stars and galaxies. This modeling is essential because it allows scientists to explore scenarios that lie beyond the realm of direct observation, helping to build a cohesive narrative of cosmic evolution. Moreover, scientists investigate the distribution of large-scale structures like galaxies and clusters of galaxies in the present universe. Observing how these structures formed and evolved gives clues about the initial conditions that guided their growth. For instance, the distribution of dark matter affects how galaxies cluster together over time, leading researchers to infer characteristics of the early universe based on current large-scale structures. Researchers are also turning to gravitational waves, ripples in space-time caused by massive events like black hole mergers. Detecting these waves opens a new window into high-energy processes that could have occurred in the very early universe, adding another layer of understanding to conditions that shaped our cosmic history. By synthesizing direct observations, theoretical models, and emerging technologies, scientists continue their quest to unravel the mysteries of the early universe, revealing the profound and intricate story of our existence among the stars. The density and temperature of the universe during its infancy were pivotal in determining its evolution. A mere fraction of a second after the Big Bang, the universe was an incredibly hot and dense environment. Temperatures soared to trillions of degrees, causing matter and energy to coexist in a unique state known as a quark-gluon plasma. In this state, the fundamental particles, quarks and gluons, roamed freely without being confined within protons and neutrons, marking a time when the fabric of the universe was still being woven. As the universe expanded, it cooled significantly. This cooling allowed the quarks to combine and form protons and neutrons. Approximately 3 minutes post-bang, the density of a universe enabled these particles to undergo processes that led to the creation of light elements such as hydrogen and helium. This era is known as Big Bang nucleosynthesis. The proportions of hydrogen and helium formed during this epoch would go on to play a crucial role in the development of stars and galaxies. The interplay of density and temperature set the stage for the universe's large-scale structures. Conditions that prevailed allowed gravity to start clumping matter together, leading to the formation of stars and galaxies over the billions of years that followed. A higher density meant that regions of space could attract more matter, becoming denser and eventually collapsing to form celestial bodies. Conversely, regions of lower density would expand and cool down, resulting in voids between galaxies. Understanding the early universe's density and temperature helps scientists decipher cosmic microwave background radiation, the afterglow of the Big Bang. This faint radiation, observed today, carries the imprint of the universe's state when it transitioned from a hot, dense environment to the colder cosmos we see now. By studying these remnants, we gain insight into the conditions that shaped our universe, enriching our understanding of cosmic history. Quantum mechanics offers a remarkable lens through which to explore the nature of reality, especially when considering conditions that may have existed before the creation of the universe. At the quantum level, the universe is fundamentally different from our everyday experiences. Instead of fixed states, particles exist in probabilities, capable of being in multiple states simultaneously until measured. This phenomenon prompts us to think about existence itself. If particles can fluctuate and take on various forms, could the fabric of reality before the universe's birth have been a vast sea of probabilities rather than a concrete state? This idea aligns with the concept of quantum fluctuations. In simple terms, quantum fluctuations suggest that even in the emptiest regions of space, energy can spontaneously appear and vanish, leading to variations in energy levels. Such fluctuations might have contributed to the birth of the universe, potentially giving rise to the Big Bang itself. Before that grand event, one might speculate that the universe did not exist in a traditional sense. Instead, it may have been a latent potential, an unmanifested collection of quantum states yearning to coalesce. Furthermore, theories such as a multiverse contemplate that our universe is merely one of countless others existing simultaneously. In these scenarios, a quantum realm pre-exists our universe, where different physical laws or constants could generate numerous realities. Each variation branches off in an infinitely vast and diverse cosmos, challenging our classical understanding of existence. If our universe sprang from such a realm, the implications for understanding time, space, and reality itself become monumental. Tapping into quantum mechanics might allow us to navigate the mysterious terrain of what lay before creation. It raises profound questions. What does it mean to exist? And how do probabilities shape our experiences? By expanding our understanding through the prism of quantum theory, we inch closer to deciphering the enigma of reality itself and perhaps the very origins of everything we know.